Switching gears, instead of discussing more angle-arc relationships, we're going to discuss segment length relationships regarding circles. And these ones have a fun name. They're called the power theorems. And we could derive these theorems using properties of similar triangles. But we're going to skip the derivations today. And the first power theorem that we're going to learn is called a chord-chord power theorem. And that is, if two chords of a circle intersect inside a circle, then the product of the measures of the segments of one chord is equal to the product of the segments of the other chord. In other words, if I have these two chords here, and I take the length of A times the length of B, that will be equal to the length of D times the length of C. Where the chords intersect, divide each other into two segments per chord, and the product of the segments of one chord is equal to the product of the segments of another chord. Now, the way we would derive this would be to make two triangles. You'd show that the triangles are similar, show that the sides are proportional, and then use the means extreme product theorem. We're not going to go through the proof, but that's how it could be done. Yes?
How can you possibly shorthand that theory?
Other than knowing that it's the segments of one, you're never going to have to write out that theorem. Okay, this is not going to be used in a proof. You're going to use this as a method of finding missing lengths. So don't be concerned about trying to write that out. Okay, because most likely you're not going to have that in a proof. Okay. The next one also can be proved using similar triangles if you were to draw in these segments. We're not going to do the proof, but this is called a tangent-secant power theorem. And that is, if a tangent segment and a secant segment are drawn to a common external point, to a circle. It's getting a little messy here, but don't worry. The square of the measure of the tangent segment is equal to the product of the measure of the entire secant and its external part. And like we just talked about, you probably will never have to say that or read that or write that again. But you do need to understand it. So in this case, here is the tangent segment. And the square of the tangent segment is equal to is equal to A times the whole thing, A plus B. Its square of the tangent segment is equal to the product of the measure of the entire secant and its external part. So the external part would be A, and the entire secant would be this whole segment. Oops, I used the wrong color. No, wrong color. Let's use pink. Okay. And so the way I like to memorize this is that it's the little bit squared equals the little bit times the whole thing. That's how I think it out. That's how I've always memorized it, but it's up to you how you want to memorize it. The square of the outside part equals the outside part times the whole thing. That's for a tangent secant. We only have one more to learn. Skipping the proof. Once again, it would be proved using similar triangles after you draw in those segments. We're not doing the proofs, but this is for a secant-secant power theorem. Secant-secant. Alright? This is if two secant segments are drawn from an external point to a circle, then the product, this is getting a little wordy, but the formula will be easy. Product of the measures of one secant segment and its external part is equal to the product of the measures of the other secant segment and its external part. In other words, the part outside, which will start with A, times the whole thing. A times the whole thing. How could we represent the whole thing? A plus B is equal to the little bit outside, C, times the whole thing, C plus D. And we'll use blue. So a secant-secant relationship is kind of similar to the tan-secant, except that in the tan, there's no part inside, so you square the part that's outside. And if you're interested in how we derive these, it's like I said, it's you prove the two triangles equal, these overlapping triangles. And if you're very interested, I would definitely show you. But I'd like to move on to the practice problem. So to go ahead and turn the page, but keep those pages handy. So let's first identify number one. What type of one is this? Is this, oh, lots of hands up. I love it. Joel. It's a chord power theorem. So that means the pieces, you multiply the pieces, and it's equal. So we could say that 2 times 6 is equal to what? Well, it's not 7x because this 7 is for the whole thing. How could I write an expression that represents just that part? Ruby. 7 minus x. So we're going to get into some algebra here. So it's going to be x times 7 minus x. You guys see how I set that up? In the chord power theorem, you multiply the pieces of each chord times the pieces or the segments of the other chord. So we have 12 now is equal to distributing 7x minus x squared. Oh boy, we get to solve a quadratic. Getting you guys ready for Algebra 2. Yeah. So we have a negative x squared. I like to keep the x squared positive. So let's move everything on this side over to the other side. So I'm going to make that positive x squared minus 7x plus 12 is 0. All of our quadratics in geometry always factor, so no problem. Who can think of the factors of positive 12 that add to negative 7? Senna? 4 and 3, but what about our signs? Yeah, they'd both be negative, right? So we have two solutions, 3 and 4. And in this case, I don't think we can eliminate either. Let's test it. 2 times 6 equals, if x is 4, then the other part would be 3. That's right. 2 times 6, if x is 3, then the other part would be 4. So they both work. And that's fine. So the setup is crucial because I'm probably not going to give you a ton of ones that involve quadratics, but the setup is the same for all of them. Okay, so we have a tangent segment PR, and the other segment is what type of segment? The tangent secant. So go back, look at the formula for tangent secant, and raise your hand if you can tell me how to set this up. Ian?
6 squared equals x times x plus 5.
Perfect. 6 squared, the square of the tangent equals the little bit on the outside times the whole thing, which you have to add up the two segments. Once again, we're getting a quadratic just for fun. So square this, distribute your x. Let's keep the x squared positive, so subtract over the 36. And let's think of the factors of negative 36 that would result in a difference of positive 5. Max?
9 and negative 4.
Perfect, I agree. So positive 9 and minus 4 are your two factors. So Jackie, what would my two solutions be? Is it possible, Jackie, that we could have negative 9 be a segment length? No. Good. So this is the one we're going to get. Lovely. Any questions so far? Okay, you're going to like number 3 because the algebra is easy. All right, so here we have a secant-secant. Go back and look at the rule for secant-secant and try to set it up. Nikki, how are you going to set this one up? Good. Good. Now this one's nice because we don't have our x's on the outside. It's when you have x's on the outside that result in quadratics. So here we get to distribute. And on this side, let's just add 4 and 8. And call that 12 and multiply it times 4 and get 48. Now the algebra is super easy. No quadratic necessary. 3z is 39, so z is 13.
Wait, what?
Because
Oh.
you subtract the 9.
Fun! Alright, let's do a couple more. These ones, unfortunately, are back to quadratics. Your homework doesn't have a lot of quadratics, though, so fun for you guys. Questions on how we set up 3? This is just memorizing a formula, right? Yeah. It's just a bummer because we have so many formulas in this chapter. But you guys are going to start your studying tonight instead of waiting until Monday night, right?
Of course.
And if you start studying tonight, then, you know, no problem. All right, now number 4 doesn't look like much, but we need to draw in some segments. And there's a couple different methods we could use to solve this because it didn't draw the segments for us. So first, I'd like you to draw the secant. It's not really a secant. It's really just a segment from the center to point P. And drawing in the radius. Now using this method, we know, where is there a right angle? Victoria. Exactly, so there's a right angle there. If we use this method, then it's not something we learned today. Let's go ahead and do it. What's the length of OT? 12. And then what's this length here? Well, yeah, you know this whole thing must be 13, and that little part is 12. So it wants, how far is point P from the circle? Well, we're done, right? It's well, from the circle, yeah, so it's 1. It doesn't want from the center, I guess. It wants that little part. PO is 13 from the circle. They should be more clear. I will always say from the center or from the outside of the circle. That can be confusing. And then this little part is 1. That was pretty easy. Well, you could also do it the way we learned it today, and you'll get the same answer. So now, connect, where did I do it? Oh, here. Oh, we don't need to draw anything else. We know that this is 12, and this is 12, right? And we call the outside part x. So now we have a tangent secant. Go back and look at the formula for tangent secant, and try to set it up. Ian.
5 squared equals x times x plus 24.
Hold on, I messed up. 5 squared equals x times x plus 24. Perfect. Equals the little bit times the whole thing. Lovely. Now this is obviously going to be a little bit harder of an equation to solve. When we drew it like this, we got to use triples. But it really just depends how they draw it and how you see it, right? So 25 equals x squared plus 24x minus the 25 over. You guys are going to be good at solving these quadratics. You're going to get to the upper school and they're going to go, who did you have for geometry last year?
Just got mine.
Yes, but if you're not good at them, tell them you had somebody else. All right, so how does this factor? Jackie? Good. So plus 25 and x minus 1. So we have our two solutions. Obviously, we're going to disregard the negative 25. And 1. Oh my gosh, we got 1 over here and we got 1 over there. So either method results in a correct answer. All right, you guys, nice job.